we have Nikos and Martin with Unstoppable Apps, Light Clients, and Parachains.
Okay, so hello, welcome to the workshop Unstoppable Apps, Light Clients, and Parachain. My name is Nikos. I am a JavaScript application developer at Parity. And since I started in Parity, I joined a team of amazing people called Substrate Connect, and I'm glad to share today with Martin what we have done so far. What we have been working on is an implementation that allows developers to quickly generate and run a light client inside their application. What is those Substrate Connect? Let's start with an introduction of what Substrate Connect is and what comes with it. As Pierre mentioned yesterday during his presentation, in a sentence, Substrate Connect is a node bundled with UI that makes it secure and convenient to use. It provides the infrastructure to run a light client directly in the browser or in any other web-based environment, from in-browser applications to browser extensions or Electron applications without any deeper additional programming efforts needed. So it comes as an NPM module that integrates a light client and supports various chains bundled in a single package. As of now, Substrate Connect supports Polkadot, Kusama, Rococo, and Westend. And if these are used, it requires no further configuration. Just to clarify here, these are the bundled chains that come with Substrate Connect, but custom chains are also supported, and we will see later on in the presentation how this can happen. Based on given parameters, it configures and returns the Polkadot.js API for communicating with relay chains and parachains using the light client to securely connect to the blockchain network. This way, the developer does not rely on any third-party owned publicly accessible node clients that are centralized and insecure, or does not have to worry about installing, configuring, and running a local node in order to test, implement his decentralized application. In addition to it, we are implementing a browser extension. Substrate Connect's extension integrates a light client and supports the same chains as mentioned before, or custom chains. And it can provide faster synchronization of chains that starts as soon as the browser window opens, and shared resources by using a small dot client. We will see a flow of what I just described in just a second. Just before that, I would like to present some milestones that we have gone through. As of January, the Substrate Connect project truly started on top of Smoldot. And by April, the first MVPs of Substrate Connect's providers were done, and the first MVP of the browser extension. In July, we managed to integrate a light client, an experimental light client in the Polkadot apps for Polkadot, Kusama, and Westend. And by September, we added Parachain support to the Substrate Connect. So right now, we are almost ready for production use of Substrate Connect and Smoldot. And we have some final touches to do, like small API changes, some polishing of code, that we have planned before the final release. So about installation of Substrate Connect, as mentioned before, Substrate Connect comes as an NPM module. So it makes it as easy, the installation as easy as and simple as installing an NPM module, of course. So for using the Substrate Connect, the first step is to instantiate the detector class. We will see in a while why it's called like that. And as an argument, this detector class receives the application's name that can be used as a metadata, for example, for the browser extension. Afterwards, there is the connect method that returns an instance of the Polkadot.js API that is configured to use a light client based on the parameters given. Here are some usage examples of the detector that we're going to see later on as well. So the connect method receives three parameters. The first is mandatory, and it's being the relay chain information, which can be either a string of the known relay chains, as we said before, that comes bundled with the Substrate Connect. So just for a reminder, it's Polkadot, Kusama, Western, and Rococo. Or you can be used a custom node by supplying an object with the name and chain specification of that custom node. Here are some examples of the parachain usage. Of course, to note here that the relay chain given as the first parameter must be the one that the parachain is connected to. So that brings us to the rest argument of connect method, which is the first one is the Parachain Specs. We pass the stringified parachain specifications to the API for connecting to the parachain, and some API options that are additional options, same as one would use to pass to the Polkadot.js API, such as, for example, custom types of the parachain. Just again, a note that we have a milestone of polishing code and slight API changes here. Now, Substrate Connect has some providers. We talked about the name detector before and its origin. So as the entry point of Substrate Connect, it was named like that because the first thing that it has to do is to detect the existence or not of the extension and prepare/configure the appropriate provider that will be used. So Substrate Connect bundles two different providers. A standalone provider that instantiates the light client in the current page that the app is running in case the extension is not installed. And the second provider, which is the extension provider, as we call it, which is used when extension is installed and uses the light client, which is running inside the extension. In the next slide, we're going to see a flow example, some flows example of these two providers. So to explain one by one, I will start with the standalone provider. So once the tab is open, the app is initialized, it is instantiate the detector class and starts to, the detector checks if the extension is existing or not. In this case, it does not install in the browser. So it initiates a light client inside the browser tab that the application is running. The light client is synchronizing with a relay, with a chain, in this case, Western chain. And once synchronized and the app is informed about that, the communication begins. In a different browser that the extension is installed, as soon as the browser tab opens, the extension starts to communicate with the known chains, which is again Kusama, Rococo, Polkadot, and Western. Once the app starts, the detector understands that the extension is installed in the browser and starts straight to communicate with the extension. And as soon as the extension starts to synchronize the moment that the browser opens, most likely it will be already synchronized and the communication is much faster. Now, for today's workshop, we created with the team of Substrate Connect a demo that would be nice to show us an end-to-end. We specified as a classified ads demo, so we're going to sell some things on a Parachain and a Western as a relay chain. So what we wanted to do show is a fully decentralized app as called as Unstoppable app, which will be the classified ads. And we built from scratch the Parachain, the ads Parachain that Martin will show in just a second, and the app itself, the UI app itself, that will communicate to this Parachain. So I'm gonna pass this to Martin for him to show how the ads Parachain was built. Hey, Martin.
Hello. I will be there in 1 second. All right. Hello, everyone. I'm Martin. I'm talking about the Parachain we made to demo the light client. This talk is going to be composed of two main parts. The first one, we're going to talk about how to code a parachain. And then the second part will be a discussion and overview on how to launch the said parachain. So the parachain we created here with the purpose of demonstrating the light client is the ads parachain. The idea is it's a decentralized classified advertising. Users can create ads, delete ads, and update ads. Also, users can post comments and update comments and delete comments. Ads are also categorized by tags. So we keep it pretty simple, but it should be compact enough that we can follow along most of the process in this talk. Now, I'm not going to go over every detail of coding a ads chain. We're gonna start off going over the high-level details, and then we'll dip down into some of the Substrate-specific Rust code. To start off with, we're going to talk about data structures. So the two main data structures that we're dealing with is the comments and ads. Comments are fairly simple. We store the author who posted the comment, the body of text that composes the comment, and a timestamp of when it was created. Ads are also straightforward. We store the author, which is an ID, and we'll discuss what the ID is more later, but the ID is just is derived from the public key of the entity or bot or that created the ad. So we have the author, and then we have a body, which is the text, and then we have a selected applicant, which is another ID. And this is for when the author of the ad goes to select someone to fulfill the ad. Then we have an array of tags. These tags are useful in categorizing the ad, and you will see them in the front end, the second half of Nikos's talk. We have a created timestamp, and which is just when it was created, same as the comments, and number of comments field. And this just records how many comments on a given ad we had. And then lastly, we have the title. So how do we persist these things in storage? We have a number of things we need to persist in storage, actually, not just the data structures we discussed. So the first thing we need, persistent storage in a parachain is all Merkleized, and it's all stored in a Merkle tree, which gets hashed, and that Merkle then becomes the block root, etc. So obviously, Merkleization is quite expensive, so you always want to minimize the amount of Merkleization you do, or Merkleize the number of things you store. Other things to note about persistent storage in a blockchain environment is everything is replicated many times. Well, replicated to the number of full nodes you have on the network. So it is reasonably or arguably makes sense that storage would be very expensive. And we also try to minimize here the number or how much we put into persistent storage. So that with that out of the way, get started with the first thing we're going to persist in the tree is the number of ads. The logic behind this I will explain in a bit, but it is important to keep that. And then we're going to store the ads in also a subtree of the tree. In this tree, the key in the tree, or the branches, the paths in the tree, will be the ad ID, which is E32, and that's going to map to an ad. Next, we will store comments, and the comments are also stored in subtree. Comments are the branches in the tree, or the paths in the tree corresponding to a comment are going to be the concatenation of the ad ID and the comment ID. And then lastly, we also store a tag index. Now this index, what it does is creates a mapping between a tag name and a list of ads, or a set of ads that have been tagged with that tag. And the reason we're storing this is so that the front end, or front ends, don't have to load every single ad from the tree to create their own index. That would be quite heavy for them to do. And if you're a light client, you're going to be requesting, all those Merkle proofs. That would be potentially really heavy. So instead, we just store the mapping in a single storage slot. And what is stored there is a Becze. And so the keys in this tree are going to be the tag name. Of course, the tag name is just going to be a vector of U8s, and that is going to map to a corresponding set, and that set contains ad IDs, which are just U32. All right. Now we're going to go over briefly on setting up and starting on writing a custom palette. We're going to follow the substrate. We're going to be based off the Substrate Parachain template. Our code is just going to go in the palettes folder. And a couple words of warning. Palettes get compiled to WASM. They probably can't use the regular standard libraries. We have to use no STD. And you can follow along using this URL. You should be able to scan. So to start with, palettes are pieces of runtime that can be potentially composed together with other palettes that form up a complete runtime of a parachain. Generally, parachains have a palette dedicated for managing accounts, currency, other things. There's several standard or base palettes you probably will need to use. If you're following along from the template, they will be included. Now, we need to bring in one extra dependency, which is the palette timestamp. And all this palette does is it gets the timestamp that is included in the block and exposes it to other palettes. Now, it's also important to note that some palettes can have other dependencies, and that sort of creates a dependency graph. So you can get stuck if you use a palette but forget to also add this dependency. So keep that in mind. And of course, they all need to be configured in the client. So other imports that we are going to use Since we're not using STD, we are going to have to use this special one, SPSTD, that Parity has created, that gives us, the standard B-tree map, B-tree sets, and Vex, for example, among other things. There's a lot of other good standard replacements in there. Yeah, we have to bring these in, and this allows us to use those algorithms. And at this point, you probably should stop and learn some Rust. It seems it is a pretty crucial skill. All right, onto building a pallet. Now, pallets are expressed as mods. They need to be public, of course, and they have this macro, this frame support macro. And what this does is it's going to go through the palette and look for other macros, and then mark that code and transform that code. So other macros that are special to pallets are like events, errors, dispatchable functions. We're going to go through some of them, but this first macro just is going to eat the whole mod or parse the whole mod and look for other macros in there. So scale. We need to use this scale codec, and this scale codec is a special codec that we use to encode and decode the data structures we talked about earlier. It is, from my understanding, created to be memory efficient and computationally efficient. It's not highly compressed. It's not like highly compressed code. It's just written to be so that you can write an encoder and decoder easily in WASM without doing a bunch of memory shuffling. Yep, the scale. Palette configuration. So palette configuration is a bit interesting. You can set any parameters if you have any parameters that your palette may use here. These are all types that come from the configured in the runtime. So, for example, in our example here, we have the event type and the currency type. Now, these are pretty standard when you use the event palette and the currency palette. So nothing surprised there. But we also have a crate fee, which we'll use later. And this allows a third party that might be using our palette to set a different crate fee. And the crate fee, as you'll see later, is just the fee charged, base fee charged when creating a ad. It's also important to note that you need a fairly substantial. If you use a crate fee too small, you won't notice that your crate fee is being used. All right, so now we get into representing our data structures that we talked about earlier in Rust code. This is a bit simplified from the actual code if you're following along, but you get the idea. So first we have the encode and decode drive attributes in a macro at the top. And this just gives the comment the ability to be encoded and decoded in scale that you saw earlier. So that is important when talking to the front end, or as a matter of fact, anytime we leave the boundary of the WebAssembly virtual machine, these data structures will be encoded at scale. So, for example, persistent storage, before they're persisted, they're going to be serialized or encoded with scale, and then when they're retrieved, decoded. And it's also important to note the front end is going to need these definitions the data structure here, so that it will know how to decode it as well. Okay, so the public struct comment, it has associated type config. We need that because when we set up the runtime, we don't set up what type the account ID is, etc. Like that gets set up in the configuration of the runtime. So that's why that associated type there is used. And that is our author, T account ID. Then the body is expressed as a vec of U8s. And then created, which is a timestamp, which we just expressed as U64. Then we have the add structure, and this is why we're all here, adds. So the add structure has the field author, which is just a account ID, selected applicant, which is an option which contains an account ID because it can either be a none as when no applicant has been selected, or can be in the selected state in which we have account. A title, which is a vec U8, a body, which is a vec U8, tags. Tags are a vector of U8 vectors. And then a timestamp, which is a U64, and a number of comments, which is a U32. And we'll get to why we have number of comments stored. And also recall that we have number of ads stored globally in a storage slot. All right, so here, this is how we express the layout of the actual Merkle tree. We have a macro, is the way all great things start with, pallet storage. So what we have, this type that we're going to have here is num of ads. This is going to be the number of ads in our storage. And that is going to be a storage value. The value that's being stored is U32. And if you look at the end, the last parameter there, we have number of ads default. So that is a function that returns the default value when there are no ads, or when the storage slot has not been set, sorry. So we'll see that in a bit. Then we have another storage slot, tags. Tags are a storage value, just like the previous example, number of ads. Tags are a single storage value, and this is where our tag index or map is stored. And as you can see, what is being stored is a B-tree map, and the key in the B-tree map is going to have a type of a vec U8, that's the tag. And then the value of this map is going to be a B-tree set, and that set contains U32s, which correspond to the ad IDs. And then we get into the ads. So ads is a bit different from the previous two examples. It is a persistent storage item, but it is a subtree in itself, right? So it is a storage map. So we have a key and a value, and that key is going to be a path along a Merkle tree. And the interesting thing about storage maps here is we have 3 parameters here that are interesting. The first one being identity, and then the second one being U32. The second one, U32, is going to be the key in this map, and that is an ad ID. And the last thing is the value that's being stored in the map, which is going to be the add type or add struct. Now, the identity is a hash function, and that hash function is used to hash the key before storing the associated value in the Merkle tree. Now, the reason we're using the identity function here and not a proper cryptographic hash function is because we control the ID of the ads. And the way we do this is by storing the number of ads, as we discussed earlier. We'll start with the storage slot will be initialized to 0, and the first ad created will be derived from loading that value and set equal to that value. So the first ad created will have ID of 0, the second ad created will have ID of 1, and this will continue to be incremented every time an ad is created. And since we control the key in this map, we don't need to worry about a potential attack vector, which that hash function was designed to protect against, where an attacker would fill out one branch of the tree, put a very, very long key in there, and maybe a bunch of storage values with a similar long prefix as that key, which then would the attacker would load, would do operations that would load this super long branch that would cause the client to come to a screeching halt because it would be so slow since it would be so deep. We don't have to worry about that though, because we have a optimal tree here where each ad created is just a single integer figure, and we don't have to worry about attacker creating a super deep tree since it doesn't control the key at all. All right, comments. Now comments are also stored similarly. It is stored in a double map. A double map is kind of like a regular map, except there are two keys. And if you look here, we have identity, which is the hash function for the first key, and then U32, which is going to be the add ID that the comment has been placed on. And then the second function is an identity, and second hash function is identity. And the second key is going to be the comment ID. And the comments tree works similar to the add tree, except we store the number of ads in, the number of comments the ad has in the given ad, and then just increment that. But we use the same algorithm to generate the IDs of the comments, so we don't have to worry about hashing their keys. And yeah, we store the comment. Initializing. Here's how we initialize. This is the initialization function for number of ads default. It is a U32. Now we have the palette errors. So errors are an enum, and the only errors that we will be using here are or our palette will be using, that whether we have an invalid index or whether the associated action is permitted. Editing a comment or I add, the author needs to be the one editing the comment or the ad. So if someone else tries to edit it, then yeah, they'll get an error, not the author. All right, dispatchable functions. Dispatchable functions make up the core of the palette. They're all labeled with the palette call macro, and we will see some examples shortly. The signatures of, so I want to sort of describe the overview so you know how like the front end will interact with the back end. So these dispatchable functions, oh yeah, I should say these dispatchable functions are callable from transactions. Essentially, a transaction always maps to a dispatchable function. So, right. So here is the signatures for the dispatchable functions that make up our palette. We have a create add that takes all. Also note, like all dispatchable functions, the first argument they get is the origin, and the origin is the signed transaction, or the signature on the transaction, from which public key can be derived. So the first one, create add. When you're creating add, it takes in a title, a body, and a tag. Probably not too surprising. Which maps very cleanly to our data structures that we discussed earlier, and it returns a dispatchable result. Now this is a little bit different than normal Rust results. Dispatchable result can only contain integer. Then on to update add. Update add contains, as you might imagine, about the same stuff, with the addition of the index that we are updating. And lastly, delete add contains only the index of the add we are deleting. We have a similar API for comments. We have a create comment, an update comment, and delete comment. These provide the same functionality, but for comments. And lastly, we have a select applicant function. This allows an author of an ad to select an identity to fulfill that it wants to fulfill the ad. So select takes in an index, which is going to be the ad index, and an applicant, which is account ID. All right. Now we are going to, I'm going to show you some of the code for the dispatchable functions. I'm going to switch my screen. It will take 1 second. It will take a few seconds for me to do this, but I will be right back. All right, you should now see some of the code for the palette. We're going to look at, so start with like, here's the full definition for the structs. We have a few more attributes in the derive macro. Also, some other interesting things are how we get the pallet ID. I didn't talk about this, but it was a little bit tricky. Pallets aren't like smart contracts in other systems like pallets, so therefore like you need to create their own ID. But let's look at these dispatchable functions because they're pretty interesting. Here is our create add, and as you see, it takes in the parameters, the ones we would expect. Here we're ensuring that we're checking the signature and then deriving and getting the author, which underneath is a public key. And then we also get the timestamp from the timestamp palette. And then we get the Pallet's ID, or account, sorry. And then we get the create fee. And this is the fee that is needed to create an ad. And then we do a transfer. We transfer from the author to the Pallet and the fee amount. And then we actually create the ad, which is pretty straightforward. And here is how we use storage. Number of ads is the first thing we're going to change because that stores the number of ads. Since we're creating a new ad, we're going to increment at 1. So it has this nice trait mutate on it. The mutate is takes in a closure. That closure is given a parameter, or has a parameter number of ads, which is the number of ads. So then inside that closure, we are going to then load the ads slot. We're just going to insert a new ad, which is going to be inserted at the number of ads, because we always, the ID in that is just the number of ads, current number of ads, and we save the ad. Then we update the tags. This is just a helper function that will load the tag storage slot, then update that map with any of the new tags. And then we have a event, and create an event that an event contains the create ad event contains 2 things: an author and a number of ads, which is the current number of ads, which is also ad ID. So that is basically the author and the ad ID. Then we increment the number of ads made. And when we increment this, this is automatically going to be stored after we exit the closure, which is very convenient. And yeah, we return an OK. Now, most of the dispatchable functions here have the similar pattern. For example, update ad, also quite similar. We use the mutate. We give we take in the ad ID, the index, and we're return back an add option, which does have to get unwrapped, but there's a helper function that we do that in. It's the check author. Check author takes in the origin and the add op, and returns the result, which is unwrapped here, and then we get the add an author back if the check has been successful. So we have check authors over every operation that the author, that only an author can do mutate on. And yeah, so that is what the rest of them look like. Comments look similar to the ad API. So no big surprises there. Yeah. Lastly, we have the select function, which is select applicant function, which is pretty straightforward. We do a try mutate. We also need to check the author. Here we do a currency transfer back to the author after the ad has been closed out, and we select the applicant. So all of these dispatchable functions have associated events with them. Now, events are actually just stored in the tree as well. So they're just a storage slot, and they store this associated information. So like update comment stores the count ID that made the update, that add ID made on it, and like the comment ID, etc. And this gives the front end a way, an easy way to look for changes made between blocks, and therefore it can make updates. All right, I am going to head back over to my slides. That will be 1 second again. All right, so you can see the code here at GitLab if you would like to look at it further. But now we will move on to deploying a parachain. Now, also, this is going to be like the previous part. I'm not going to discuss all the details of deploying a parachain, but sort of give you a high-level overview of it. What we're going to be doing is some preparation. We essentially already did the preparation, which is building it. Then we're going to talk about launching the relay chain, launching a parachain, and then profiting, which is sitting back and watching the blocks flow. So to launch a relay chain and parachain, this is all we're talking about this locally. Nikos will demonstrate our parachain running on West End. So obviously we're not launching West End because it's just local for local testing. This is, you can get a lot of detail on this this Cumulus workshop. Should you scan this code, it will take you to. It gives more detail than I'll give here, but yeah. So hopefully we have a parachain running and tested on your laptop, and therefore you're ready to deploy. We need to do some basic stuff. Clone Polkadot. We're going to clone it and check out the latest release and build it. And then we need to generate the chain specs. So after we built Polkadot, we have to use the build spec command and say which chain we're going to be using. Locally, we're just going to use local. Pipe that out to a JSON. And then our parachain correlator, which we built in the first half of the presentation, we're going to do the same thing. We'll say we're local, but we can say other networks if we want. Produce a chain spec. Now, this chain spec will be important later. So we also should remember to give it to Nikos. The front end, the light client will in particular use the chain spec to know how to connect to our parachain and sync with it. So Polkadot has these convenient, next we have to start a relay chain, which is going to be the Polkadot node. And to do that, we're going to start two nodes, Alice and Bob node, as validators. And luckily, Polkadot has this nice feature with Alice and Bob flags built in. And this just sort of are some like pre-established keys, so we don't have to go through the work of setting up our own keys. So Alice and Bob are just underneath keys. So we're starting Polkadot in the validator mode with the base path. Base path is just like where we're storing blocks and other associated state information. The chain, that needs to be the path to the spec that we generated in the previous slide, the relay chain. And then a port and a WebSocket port. We need to specify these because we're going to be running these all locally on our computer, and we don't want them to collide. So we're going to do the same thing for Bob, the other validator, except we have a different base path and different ports to listen on. Same chain spec, of course. And at this point, you should see a relay chain running. So since they're both running locally, they can automatically find each other, and that's great. So generating next step is to launch the Parachain. To do that, we take our Parachain collator that we have already built. We need to export the Genesis state. In there, we also need to specify the Parachain ID. We are using the ID of 2000. I'm going to say that as the Genesis. And then the collator, we need to also export the Genesis WASM. This is our essentially our runtime, all compiled to WASM, nicely bundled up. And now we can start the collator node. The collator node will be Alice. We have to tell it it's collator node. We have to say force authoring, so it can just like make its own blocks without anyone else. We say what Parachain ID it is. Of course, we have to give it the base path where it stores everything. We have to set up the ports correctly. And interestingly enough now, we have 2 dashes, and then everything after those 2 dashes are going to be for a relay node. So the Parachain collator it's a collator on the Parachain, first of all, but it also runs a relay node internally, and all the arguments after the 2 dashes are for the relay node. Relay node is going, we want to say it's executing WASM. We want to give it the chain spec of the relay chain, and of course, set up the ports once again. And then everything should be running. And then we have to use Polka.js to actually register the Parachain. So to do that, we head over to the developer tab, and we have sudo access, which is great because it allows us to easily get one of these Parachains up and running without much hassle and to debug it because it'll probably be broken. So first thing we need to do is select para sudo wrapper, and we're going to do a sudo para schedule para initialize, and we give it the ID, which is going to be 2000, on the Genesis arguments. And the Genesis arguments are going to be the Genesis state and the WASM. Lastly, we want to select, there's a bool parachain. When we select the yes here, we'll make a parachain. If select no, we'll make a parathread. But we would like to make a parachain. We'll select that. And then with that, if we submit that, we'll have a locally running parachain, which is great. And that is it for now. I am going to pass it back to Nikos, who's going to do the rest of the demo. Thank you very much.
Thank you, Martin. So as Martin showed, he built a Parachain for the unstoppable app that we want to build for classified ads, and he explained the ads, the comments, and everything that needs to be done. So the purpose, as I have said already, is to build a fully decentralized app. So to do that, again, the custom Parachain created from Substrate using Cumulus. We're using the Substrate Connect, communicating with that Parachain using an integrated light client, and to be fully decentralized, we deployed it in IPFS. So just a reminder before we switch to the demo and the code, for running the, can hide this somehow, for running the Parachain inside our application, we need to initialize instantiated detector, pass the name of the application, and then use the connect method in order to pass the relay chain that we are connected to, the Parachain specifications, and any custom API options that we may need. Before jumping into the code, I want to switch to the West End in Polkadot.js apps in order to show what Martin has done, which is our parachain with the ID 2000. We can see it here being registered in West End. And on the Polkadot.js apps, if I switch to the parachain itself, I can see blocks being released, created. So I'm gonna switch now to the code before jumping to the demo. As Martin said, he provided me two things. One of them is the chain specs, which is, before I go there, I want to say that we built our whole React app, and we got from Martin the chain specs and the types that he wrote, the custom types that he wrote in order to use. So the chain specs is this file that contains the boot nodes and the collators that are set up from Martin, the ID and the name of the parachain, and most importantly, the relay chain and the parameter ID. The ID of the parachain, which is the 2000 that I just showed you. Now, the types that Martin described, we created a JSON that contains these custom types in order to pass them to our API for being able to decode the requests that we're receiving. And finally, we created a service layer in order to consume the API once it's connected. And that service layer, with this service layer, we hide the domain logic from the application. So in this service layer, we are importing the definitions, the custom types we just see. We're importing the Parachain spec, and we're importing the detector class from Substrate Connect. And with just 2 lines of code, we are, as shown on the slides, we are just initiating our detector with the name of our application called classified ads. And we are running the connect method with the relay chain name, which is West End. This exists bundled with the Substrate Connect, so we know which one it is. We're passing the parachains, we stringify them, and the custom types, and we are receiving the API that is going to be used across the application. I'm going to switch now to the demo, and let me try to, to run it here. Okay. So right now the small dot provider is initiated, and it's initiating inside the browser. The live client, because we don't have extension installed in this browser. As said before, the IPFS we deployed the application in IPFS IO, and and we are connected. We received the ads that exist on the parachain, and as we're using the dev accounts that have some units to play with. And what we can do now is, let's first of all use the create a new post with, let's say I want to buy some pizza, and add some tags, and then say I want to sell some pizza, and we'll say selling pizza. So we're posting that, and we will see a notification that's saying that this action happened. Until it arrives, I can say that we have also having the APIs that Martin provided. We can search through the tags and find the ads we are interested in, like sort them, or we can see only the ads of the current user who created the ads, or only ads that comments are created. Not sure why we're not receiving a feedback, but I'm going to switch to another window. So here we can see the last events that has happened on the Parachain, which is a create comment from Alice or a create ad, and balance transfer that's happening on the Parachain through the application. And here is what we should see in the other window that we didn't, which is comment submitted. And if we click the see transaction, we can actually see that a create comment happened, and probably also the, yeah, I'm interested of the comment. I will give it another try here to create a post. Yeah, this worked just fine. So the ad is submitting right now, and in a few seconds, we're gonna see the decoded response arriving in the UI. Yeah, I will just wait a few seconds if this works. I'm not going to wait anymore. So, oh, it did work. Here it is. So the ad is submitted. Here is the block hash. We can go to see the transaction, and here is the ad that was created on the custom Parachain. I'm going to switch back to my slides now. So this is the demo that was we built for the Sub0. And in order to play with it, you can use the QR code on the left, or if you want to see the GitHub code, which is public, you can use the QR code on the right or the link. And last thing I want to talk about is the Substrate Connect extension, which I have running few demo apps running on the background, and I just want to show how the pop-up is working live and how the options are working live. So if I switch to the window that I have some tabs running things, we can see here, I'm gonna close this one. We can see here that the extension is having 4 different apps running and showing which app is connected to which network. The Parachain demo here has an exclamation mark because the extension doesn't know this chain, while the rest ones, as we have talked before, are known. And if we go to the options page, we are at this, we can see which networks are connected in the extension and what is the status of the live client, the name of the network, if the chain is connected, how many peers, how many apps, and which apps are connected to that. In order to see more, here are some useful links. You can see the code of Substrate Connect in GitHub. Again, we are almost there. You can find a landing page of Substrate Connect with more details and links and documentation links, and the npm.js link for downloading and using the Substrate Connect. So that's my part of the presentation. Thank you so much.
Yeah, so I've got some questions for you from the audience. So the first one was someone asked, why do you need to specify the weights individually for each function? Could you just do that globally?
Possibly if all the functions were similar enough. Yeah, but that was just not something that, yeah, I looked into optimizing.
Yeah, I guess, each function has different does different computations, and so it's going to have different weights, and so you'll have to specify them specifically. Although I guess for this example, yeah, you could just give them some arbitrary number. So someone asked why you didn't use a GUID, like a globally unique identifier, instead of using the add number as its own key. I'm guessing this is just to make the code simpler, but was there another reason?
Yeah, it was a toss-up between that and using a globally unique identifier. But so if you have short, ideally, or the original idea was if you have the shortest key possible, they're all U32s, but like you could, in theory, trim them down into bits if it was a bit string, and then you would have very short compact keys instead, and like globally unique IDs would probably be like 32 bits or something, but size of a hash function, output of a hash function. And then you could construct a very compact binary tree. Now the demo doesn't go into all those details. It uses the default trees, and it doesn't attempt to compact the keys. But given a more complex and larger project, it might make sense to go into doing those optimizations where you split the key up into actual bits and then have very short, compact keys.
Okay, yeah, thanks, Martin. So another question, would it be possible to also store author or machine-generated keywords so that you could do some form of decentralized search on your chain?
Yeah, sure, you could. But I mean, it's always a trade-off of like how much you want to store on chain. It might be better to just store hashes and some sort of proof that of the data set instead of trying to store that all in regular storage, depending on how big your data set gets.
So Nikos and Martin, thank you very much. We appreciate you coming on.